Hey, welcome back. This lecture is going to be on tries, which are section 8.2 in the textbook, the blue textbook. Tries are going to be the third structure we look at that is based off the idea of what the book calls digital data. So we had looked at comparison-based structures extensively, and that were things like AVL trees and B trees, where the less than operator was the key comparison unit that allowed us to insert and remove and so on. And when we talk about digital data, we're usually referring to some kind of a type where there is something else besides comparisons that we're dealing with in terms of trying to categorize these types. So we looked at the bit vector, which said, and it's not so much comparisons we're worried about, but instead we want to be able to enumerate the type. And we looked at hash functions, which said we're not really worried about comparing one element to the next, but we are worried about hashing on the key to get an index. And now that we look at tries, the worry here is going to be being able to break down our type by character. And the best example of this is a string. Can talk about having characters in positions, say 0 through 4 for this example. And so in addition to the whole string being a type, we can say, well, the string is composed of individual characters, and those individual characters could be retrieved. And we may even say, and in fact we will in our examples today, the \0, the null character, is generally a character at the end of a string that we wouldn't count in the length, but it is there to end the string, so as you traverse across, when you hit the null character, you know you've hit the end of the string. And so the idea there is then that when we have a type like that we can break down by character, there are interesting ways of storing it. Another example might be some sort of 32-bit binary number that we could view as, say, clumps of 8 bits. And so a 32-bit binary number could be thought of as a 4-character type, where the first character is your 8-bit number from 0 to 255, and your second character is an 8-bit number from 0 to 255, and so on. And there's 4 of those 8-bit characters making up a 32-bit number. So certain kinds of data could be broken up character by character, and what we're going to look at with tries is a means of storing and accessing our values of our type that involve breaking the type down into its component characters. And the key idea behind this is going to be an array, where we say here if we have an alphabet of size k, then we want a k plus 1 cell array. And in effect, what we're going to be building here is a k plus 1 array tree. And from your discrete math course that you presumably had before this, and if not, then I think I mentioned it in the tree lectures too, the idea of a k array tree or whatever, something array tree in general, where the number before the array is the number of children. So we had a binary tree was a 2 array tree, and a 3 array tree would have at most 3 children per node. And so a k plus 1 array tree here is a tree, just like we've seen before, but it'll have at most k plus 1 children per node. And those k plus 1 children are going to be indexed in an array. And so we'll have here various pointers, of course, to actual subtrees, because that's how trees work. And every node then, unlike the binary tree, whose root node had 2 pointers to subtrees, here we have a node that has 27 pointers to subtrees. And so each of those then would likewise branch out in a maximum of 20, for an English alphabet, 27 different ways, because there's 26 characters. In general, k plus 1 array ways. And so we're talking here about k plus 1 cells. And each of these cells are going to represent a character. So for example, if we're dealing with the English language, and so k is equal to 26 for the letters A through Z, we have here A and B and C and so on. And I'll get into what the 27th symbol would be in a moment. But the idea then is that we set up an array that has the individual characters as its indices. Conceptually, we'll talk about how that actually works in a moment. And then what you want is, let's say your first word you want to look up starts with the letter C. Well, you know it's going to be stored in the subtree that C points to. And so more generally, write these words down because I'm not going to be able to fit them on the next. Actually, maybe I will. Let me try this. We can have here, we're going to insert the words car and cow and top. And so we have a root pointer, as always, for a tree. And this root pointer here will be composed of a number of pointers. And here we'll have our C pointer, and here we'll have our T pointer. And this will be level 0, because we're looking at the 0th character for the string. Remember, I had written on the previous slide, generally, just like for regular C++ arrays, when we're counting characters in a string, we'd start at character 0 rather than character 1. And so we'd have character 0 there would be an S, and that would be what we're looking at. And so likewise, when we talk about the trie, we'll have the character indices correspond to the depth of the level you're on. And so, of course, at the root, you're at depth 0, and that corresponds to character 0. And so at depth 1 here, you are then worried about looking at the character in position 1. And so everything that this pointer points to is the collection of things that start with C. And out of all of those things, some of them start with A, and some of them start with O. And so you'd have here a subtree of things that have C in character 0 and A in character 1, and a subtree of things that have C in character 0 and a O in character 1. And then here you'd have your subtree of things that have a T in character 0, and we haven't really dealt with anything there yet. So we're going to finish filling those in a moment. But this will be the idea behind a trie, where we'll have our top node is indexed by a particular letter, and so then we traverse down this structure. The other pointers here, and I'm not going to draw all of them, and generally I'll just draw things like I've drawn them here. Any characters I haven't written in are assumed to be null. So we have here A is null, B is null, D is null, and so on. And so those would be the characters as we deal with them, and so on and so forth. And so that's the idea then. We have a car is C in position 0, A in position 1, and then an R in position 2 means we point there. Cow has a C in position 0, an O in position 1, and a W in position 2, so that node would be found there. And top has a T in position 0, an O in position 1, and a P in position 2, so that's to be found in that subtree. And we haven't finished those off yet, we will in a moment, but those would be the 3 subtrees that these 3 words would generate. This is the CAR subtree, this is the COW subtree, and this is the TOP subtree. And so that gives us a trie to deal with. Now, when dealing with this trie, we have a few things to worry about. And one of them is, how fast does this look up down the tree? And so one of the things that we have to worry about is saying, given a string, if my string, let's just go ahead and declare it string S, and maybe as an argument to the constructor, we pass car. Just so you have some idea of our data type here. Now the question is, how fast can we extract a character from that string? And you've already used the string class, and though you may not have used this particular feature, if you look at the string class you've been using all along in your MPs, you will notice that we've overloaded the bracket operator, making it possible to go ahead and return, using indexing, individual characters, where S of 0 is going to be C, and S of 1 is going to be A, and so on. And of course, array indexing tends to be constant time, and indeed it will be with our string class, because the string class is just implemented with an array of characters behind the scenes. And so if you pass in the index, you get the character, and that means that that's going to be constant time. Indeed, in other languages, it's the same thing. If your S was a reference to a string in Java, not that you need to know that for this class, but Java does not allow operator overloading, but there is a char at function, and you'd pass in 1 and you'd get the same thing. So the idea would be whether it's Java provides a method that behind the scenes will do the exact same thing, access the character array implementation. And so just as in C++, other languages will tend to provide a constant time facility for accessing string characters as well. Not every language, I suppose, but a lot of them would. And so that would be the idea there. You've got then the ability to extract characters from the string in constant time. And so that's part one. Now, of course, now that we have this character, the difficulty becomes, okay, I've taken ka or cow or top, and I've grabbed a character from it that I want. And then how do I find the appropriate pointer in the array? And here we have the idea that you've already been seeing on the news group a little bit with regards to the current MP, where you're dealing with the ability to go ahead and add characters. And the reason is there can be a cast from a character to an integer because there's the idea of, and you may have heard of this, ASCII, which is a standard table of translations from characters to numbers. The idea, of course, is when you type a character on the keyboard, the hardware itself can only store ones and zeros. And so what you need is the ability to represent a character as a number because the computer inside can't store the letter C or the letter X. It needs to store a pattern of bits. And so there is a standard agreed upon way, at least in the Western keyboard characters, for those characters to be translated into bit patterns so that everyone's using the same bit pattern for the characters, and that makes interoperability easier and so on. And now that's been expanded to Unicode for international character sets. But the basic idea is things like, oh, the little a maps to 97, and the little b maps to 98, and so on. And I believe the capital A maps to 65, and the capital B to 66. Anyway, the point being that the designers of ASCII were clever enough to say, well, our sequence of characters, all the little characters in a row, from little a through little z, or lowercase a through lowercase z, will be consecutive numbers. And the characters capital A to capital Z are likewise consecutive numbers. And so what that gives us the ability to do, and you can go ahead and write in the explicit cast if you want, is I could go ahead and say, well, take my character S of 0 and cast it to an integer. And then, oh, let's say if I'm dealing with all little letters, we'll assume that for the moment, subtract 97. And that expression gives you your index, because if you've passed in if S of 0 is the lowercase a, well, that casts to 97, and in general, you'll be able to just assume the cast is automatic, like you may be dealing with in MP7. And then you subtract 97, you get 0. If your character had been little b, you'd cast it to 98, subtract 97, and you'd get 1. If your character had been little c, you'd cast it to 99, subtract 97, and you'd get 2. So you can pretty much set up an expression like that that basically says whatever my character is, cast it to the appropriate integer, and then subtract 97, and that'll give me an index from 0 through 25. I can go ahead and write that here. So each of your arrays in your trie, each of those nodes, could be an index from 0 to 25. And that takes care of 26 of our 27 children. Keep in mind as well that if we wanted to deal with capital letters, we could have done something like this. You could have just said something like int x equals cast, the particular character, and then you can say if x is less than 97. If you assume you're dealing with capital or small letters, if x is 97, then you know it's in the range 65 to 91 or whatever the range of capital letters has to be, and then you could say some sort of index equals x minus 65, and then you could say otherwise, and then the assumption there is that you're in the range 97 to 122, or whatever the range of the small letters is, and then you say index equals x minus 97. So you can do something like that as well. And that would give you the ability to say, well, whether I'm holding a capital or a small letter, I can quickly take care of that. Give me a moment here to change the battery in the microphone. Okay. So the point here is that this is constant time, even if we have to check for capitals versus small letters. And so that takes care of, we're going to assume for the sake of examples, only small letters. But if you wanted to, you could do with capital letters as well. And if you wanted to index by capitals or small separately, you could have an array of size 53, 26 plus this extra last character we have to talk about. But the idea there then is, I could have mapped this from 0 to 25, and by subtracting to the appropriate amount, I could have mapped the small letters from 26 to 51. Anyway, the point is that this is also constant time. So I can extract the string in constant time, and I can map it to an index in constant time. And of course, once I have the index, I can jump to that spot in constant time. So in our example here, we're dealing with small letters. I've written capitals to make them, I've written capitals to make them easier to read, I guess. Though I don't know if it does make them easier to read. But at any rate, these are our 26 of our 27 cells, and I've written the character above, but the idea is this is really index 0, 1, 2, 3. The A, B, C, D are conceptual. In reality, we use an integer index, retrieving that using the method we just talked about in the last two slides, and then we jump, given that C, to cell 2. Or given the A, we jump to cell 0. So I can retrieve the character from the string in constant time. I can map it to an index in constant time. Given that index, we know, of course, we can jump to the array cell in constant time. And then once I'm at the array cell, I could dereference that pointer and get the next node in constant time. And typically what would be the case would be, certainly we could just have arrays if we wanted. More often than not, what we might do is encase this in an entire node. So instead of just simply pointing to arrays, we'd be pointing to, we have a whole, like a trinode structure. Just like we had a tree node before, we'd have a trinode structure that we'd be pointing to, and that would point to another trinode, and that would point to another trinode, and so on. And that way we could hold the array, and if we wanted to, hold the particular level and any other information we might want in these nodes. And so typically that would be how we would do things. We wouldn't just have the array. It would be part of a node. But either way, you get the idea. So that would be then, the result here is we spend constant time on each level. And that's very important. Dealing with this, we spend constant time on each level because we have the idea of constant time to retrieve a character. Character retrieval and constant time index generation and constant time array access and constant time pointer dereference. And then because we spend constant time on each level, that results then in the great strength of tries, which is, if you consider here, if I'm trying to determine whether a particular value is in the try or not, or if I'm trying to get to the pointer after the last character, I can do so in time dependent on the length of the string. If I have 3 characters, I say, well, look at the first character, look at the second, look at the third. If I had 2 characters, I'd say, look at the first, look at the second, and I'd be there. If I have 10 characters, I look at characters 0 through 9, going down levels 0 through 9, one by one, and I'm at the end of this tree. And that's not affected by how many values are inside the try. So if I had this subtree off of T had huge numbers of values, and all the other subtrees had huge numbers of values, I'm still going to say CAR and get to the car, the pointer after the R, in 3 nodes. I read the C pointer here, the A pointer here, and the R pointer here, and I retrieve those in constant time each, regardless of what other nodes are in the structure or how many of these other pointers are non-null as well. And so since it's constant time on each level, the strength here then is we have our lookup time to traverse down the entire string and get to the end of the string is going to be order L, where L equals the length of the string. And typically, even with the hash function, we'll have to traverse across the string and read the individual characters and then to be able to create some hash index out of them. And so this really shouldn't be any slower than hashing in that regard, because in the time we go here from leaping character to character in the array cells, the hashing would be reading character by character of your string to generate a hash function. And so the table lookup is itself constant time, but we, of course, if we have like a string key or something, do need to generate some value from the string itself, which typically is pretty fast to do, just like this is pretty fast to do, but there is some cost there. So in all our discussions, we sort of assumed a constant time conversion of the key to a index when we talk about hashing. And in reality, you'd probably have to parse over some of the string. And if your string sizes are bounded, you can still think of that as constant time. But likewise, if your string sizes are bounded, you could think of this as constant time too. We'll view it as on the order of the length of the string. The important thing here is it's not dependent on the number of strings in the trie, which is pretty well the first structure we've seen for that to be the case. The first structure we've seen where no matter how many values you dump into the structure, it doesn't affect the lookup time of any of the other values. Bit vectors, you couldn't really affect how many values were in the structure because you had every element in the universe in there already. You were just signaling whether they were in or not, but you had at least some space reserved for every spot in every element in the universe. And then the other structures, B trees and hashing and linked lists and arrays and so on. I guess arrays, you'd say, if I'm looking up by index, then I can look up in constant time no matter how large the array is. But that assumes that you have an index to look up by. Here, all you need is a string, and the string itself sort of becomes the index in a way. Each character becomes part of an index, and so we can, unlike an AVL tree or a B tree or something, we can dump huge amounts of values into this trie, and it's still pretty quick to look up any one value. They're not affected by how many more insertions you do. The downside to this structure is, if you'll notice here, I've got 27 pointers, and in my picture only 2 of them are non-null, so I'll have 25 other pointers, and they're all null. And we have a bunch of null pointers here, and then 2 active ones, and 26 null pointers there, and one non-null pointer, and so on. We've got these huge arrays that have been allocated, and we're tending to not use too many of the pointers. And even if we do, we've got huge arrays allocated. But in practice, we won't always be using a lot of the different pointers. A lot of them will be set to null. And so whether they're set to null or not, the downside here is we're using large amounts of memory. I've got here 27 times 6, even though I haven't even finished the bottom of this trie yet. I've got just what I've drawn here, 27 times 6 pointers, which is 162 pointers, unless I've just multiplied wrong, 162 pointers simply for 3 words. So the upside is a very nice lookup time. The disadvantage is there's uses lots of memory. And what we'll be looking at for a lot of the remainder of this trie lecture is ways in which we can trim down the memory usage of tries. But that's the disadvantage of this structure, is a lot of memory is used by this structure. But this pretty much sums up the yes and no of tries. The good part is your lookup time, the bad part is your memory usage. And so for the rest of the time, we'll be discussing sort of variants on how to set up the structure. So let's finish off this diagram now and talk about this mythical 27th pointer I keep referring to. We have an issue here where if I'm dealing with these 3 strings, okay, things seem normal so far, But what if I'm inserting into this try strings car and card? I have here character 0, 1, 2. Card has character 3. And you say, well, that's no problem. I can always say, well, I could add another array to deal with D in position 3. We'll come back to this slide. So I can say here I have the C pointer on level 0, the A pointer on level 1, the R pointer on level 2, and on level 3, let's go ahead and add D pointer. And that works all fine and good, except the problem there is, yes, now I know because the D pointer is active, I must have the word card in my try, or at least I think I do for the moment. Because certainly, what about the word cart with a C? If I didn't want, or with a T rather, sorry. If I didn't want cart in my try, I could tell that by saying, well, the T space here is null. And I didn't draw it before, but I'll explicitly draw it in and set it to null. If cart with a T at the end had been in my try, not only would the C and the A and the R pointers have been non-null, but also the T pointer on level 3 wouldn't have been null, and it would have been pointing to some other object, because we would have had here to sort of indicate here C-A-R-T. And so cart would likewise have been in position, or the T in cart would likewise have been level 3. And so we would have had that T pointer pointing to something just as the D pointer points to something. And so we can tell easily that cart with a T is not in the try. Similarly, I can tell easily dog is not in the try because the very first letter is null. And I can tell easily that cube is not in the tree because the U pointer, which I haven't drawn, but I suppose I could, the U pointer here, which we didn't draw, was assumed to be null because we didn't draw it. In reality, of course, you'd actually have the U pointer and it would be null. And so if at any point we're looking in this tree and we hit a null, well, we should have hit a pointer, then we know that value's not in the tree. So I say, well, for cube, the letter C is in there, but the second letter of cube is going to be U. And I'm just writing this out in case I don't know how clear the microphone is, so this is the word I'm dealing with. And that way, in case you can't quite make out the word, that's what I'm talking about, instead of Q. So U is in position 1. And so if cube was in the try, we would expect that U would also be non-null. And since it's not, we know cube is not in the try. And so that's sort of our not found signal. Whenever we hit a null, we say, well, the null is in the first character, or the first character exists for cube, but the null is the second character, or for cart, the first 3 pointers are non-null, but the fourth character is null. Whenever I hit that null pointer, if I'm not done looking for the string yet, and I hit the null pointer where I expect to see a non-null pointer, then that is a signal that the value is not in the try. So that's okay, as far as words like that, so far so good. The problem we have is distinguishing between prefixes, because what if I wanted to have card in the try, but not car? Or on the other hand, what if I wanted to have card in the try and also wanted car in the try? There's this ambiguity where if I store a word, I've by definition also stored the prefix. Because I need to have the C, A, R, and D pointers on sequential levels active for card, then by definition the C, A, and R pointers are active for car. And so that's the problem we have here. Even if I didn't want to store car in the try, I had to have the C, the A, and the R active as part of storing C, A, R, D. And so how do I indicate that the word car really isn't in the try, or on the other hand, how do I indicate it really is? And the answer is our 27th pointer, which is going to be the null character. And the book notates that with a small triangle, so I'll do the same. This would be our very last pointer. So we have indices 0 to 25 for the letters, and then index 26 would be this null character. And the idea then is, as I said before, usually with an implementation of strings, the system wants to be able to traverse across, in the implementation, traverse across the strings one by one. So you usually have some delimiter null character to indicate you've reached the end of the string. And so here, that would come in character for all these 4-letter words, the \0, this is an actual character, but even though it takes up 2 keyboard types, it's considered 1 character, the null character. So if you've never heard of that before, now you have. This is the character representing null, just in a sense, same sense that 0 is the sort of absence of value integer, or 0.0 for floating point numbers. Likewise here, this is your null character for characters. And so you would have the null character in the last position in each string, which for the 4-letter words is in position 4, and for the 3-letter word is in position 3. And because the null character is your stopping point, there's no way to have anything after the null character. So we don't need to worry about, what if I'm trying to store car, C-A-R, null, and then dx. And the answer is, well, that can't happen. When you see the null character, that's it. Your word is over. And so if you were to store C-A-R null, there's no danger of that being a prefix of anything else. And therefore, all we need to do to indicate for sure that a word is in the try or not is to require that the null character be stored after it. That is, for card, here on level 4, I can say I have the null character pointing to, on level 5, C-A-R-D. And so I know card is a part of this try because I've looked at all the characters. In other words, not just C-A-R-D, but all 5 characters that are part of our storage, C-A-R-D, and also null. And so if this character had been null, then I have C-A-R, but when I go to follow the pointer at the null character position, well, that pointer doesn't point to anything. That pointer is null, indicating the null character is not active. I do have a C-A-R-D, but I don't have a C-A-R-T, because T is null, and I don't have a C-A-R null, because the null character holds a null pointer. And so that would mean C-A-R is not in the try. On the other hand, if I was to point to something here, this would be level 4, would point to car. Instead of holding a null character, I'll hold a pointer to a leaf node. Then I know car is in the try, because just as C-A-R-D can be followed, C-A-R null can also be followed. And so what we're looking up when we look up a word is not C-A-R or C-O-W or T-O-P, but C-A-R null, C-O-W null, T-O-P null, C-A-R-D null. We're always looking for that null character as our last character of the string. And that way, that serves as sort of a stopping point. The null character will always point to a leaf, and the null character array cell will always point to a leaf, not some further subarray. So if the null character holds a null pointer, we know the null character does not exist, and therefore the prefix up to this point is not a word. It's just a prefix of some other word. If the null character held a null pointer, it would mean, yes, C, A, and R are active, but not because car is in the try, but simply because we need them active due to them being a prefix of something else, specifically card with a D. On the other hand, if the null pointer is active, it means whether CAR is a prefix of something else or not is irrelevant. I at least know there is a CAR null. So the word car is in the tree. Now maybe D and T were both null and there was nothing else, in which case all we have is CAR null, and that's fine. Or I can also have D active and have both CAR null and CARD null. That's fine as well. The point is simply that by having a space that's understood to be the null character, I can then, by making that active or null, by making that pointer non-null or null, I can indicate whether that prefix is the actual prefix of or an actual word in itself that's stored here, or just the prefix of some larger word. Because if the prefix isn't a word in itself, it will end at this point. And if the prefix is not a word in itself, but is simply the prefix of some larger word, then there would be no ending at this point. And so that's the idea behind the null character. And so likewise here, these could all be, we haven't ended any words here. Here I'd have the null character active, and this would point then to, this is on level 3, and here on level 4, I have COW, and here, likewise, I have level 3, and on this pointer I have, and this is going to get very small, you probably can't read this on the video, but I'm writing in top here. That's the problem with these diagrams. I've only got a small piece of paper here, so everything's sort of crunched up. But anyway, this says top, cow, car, and card. And the numbers here are 4, 4, 4, and 5. And so that's the idea behind it, that this would be a trie that would hold these 4 words. And now this is complete. And of course, these leaf nodes could hold not just the word itself, but could also hold the information. If there's some, like we're looking up, say this way, a dictionary implementation of not just the dictionary ADT, but an actual dictionary, where we're looking up a word, we want to retrieve its definition. Well, this leaf node here could hold the definition, some info, which would be the definition of the word, as well as the word itself. We can hold whatever, this is just the key, we can hold whatever info we want in the leaf as well. Typically, the leaf would work, the way the leaf could work would be in the same way the B tree node worked, where I said I can have a B tree node that can toggle between being a internal node or a leaf node, depending on some flag setting within the structure itself. And likewise here, we have the idea of this node could say, well, if it's an internal node, allocate this array. Otherwise, and maybe a flag is set to 0. Otherwise, if it's a leaf node, then set the flag to 1. You don't allocate the array, but you do have a string pointer that can point to your key string, and so on. And so you can have here that your array cells always point to trinodes. Sometimes the trinodes are set to be internal nodes. Sometimes they're set to be leaf nodes. And so you'd have in every trinode a pointer to an array and a pointer to a string. And so the pointer to the array points to an actual array if it's a internal node. And instead, that array pointer would be null, and the string pointer would point to a string if it was a leaf node instead. So that way, you can always say, well, I'm holding an array of trinodes all the time, rather than saying, well, how does sometimes it points to an array and sometimes it points to a leaf of some kind? The answer is the array and the leaf could be the same node type, and you simply use a flag to distinguish which one is which. So the other thing I want to mention is that we don't need to store the words. If your only concern here is as a lookup structure, let me just redraw this node again. If I have here this situation, I'm looking for car, and here's the R, and then here on level 3, I said, well, I'm holding card as well, and then here's this. As long as this is not null, we know car is active. So I'm going to write a G there for the word garbage for the moment. As opposed to what this could have also been, would have been looking like that, where D actually holds null. Now, we said before, if we come across CA and then follow the R, this is a close-up of the other page, and then when we look at, on level 3, the null character, and it turns out that the null character holds a null pointer, well then in that case, we would know that the since it holds a null pointer, CAR null is not in the tree. In this case, since that pointer is not null, we know that CAR null is in the tree. And the previous slide, we actually had, instead of a garbage value, we had a legitimate address to a legitimate leaf node. However, if we weren't concerned with storing any keys or information, if the only purpose here was to say, yes, the key is in the tree, or no, it's not, then technically we don't simply need to have a non-null pointer there. We could say, when you encounter, in the other page we said, when you encounter a null character that's not null, You can follow that to get to the leaf node containing the word, the info, and so on. If we had no intention of following that, then we don't need a legitimate pointer. You don't usually want to store garbage, but you could get away with it here if you wanted to, because you could say, well, I don't intend to follow the pointer at the null character. I know it doesn't point to anything real because it's garbage, but that's okay. It's okay if it holds a garbage address. I'm not concerned with dereferencing that to get a node because I'm not concerned with storing anything along with this key. I simply want to know, is the key in the trie or not? And so we could simply say then, if I read a null there, I know CAR null is not in the trie. If I read some non-null address, I know CAR null is in the trie. And I could stop there. So if your only concern was membership testing, then as long as you were willing to be very careful not to go ahead and follow that garbage address, as long as you weren't expecting the null character cell to point to anything legitimate because you're not concerned about reading anything else, you simply want to know, hey, the null character isn't null, that means the prefix up to this point is indeed in the trie. Then you could store a garbage value there, and that would be all you need to worry about. You wouldn't need to actually hold some node that simply held the same key you just confirmed was in the tree anyway. So if your only concern is membership testing, you technically don't need the leaf nodes, and so if you're willing to be careful and not follow that address, you simply need to use null versus non-null to distinguish between whether CAR null is in the tree or CAR null is not in the trie. But typically you'll want to hold information with your keys, and so you will want to follow that address to a null pointer, and so it should be a legitimate address. But that's just sort of an efficiency trick. If you didn't have any need to store leaves, as soon as you know this is not null, you could stop at that point and say, yes, CAR null is indeed in this trie. And you wouldn't need to follow that pointer to confirm that. The fact that it's not null confirms it for you already. Following the pointer only gives you additional information now, like, oh, here's the info associated with that key, or whatever else. But the membership test is signaled yes as soon as you know that pointer isn't null. So technically you could get away with storing garbage there, but generally it's not the safest thing to do, but if you're careful, you could get away with it there. And so that is your trie structure. Now, there's a few other things we can do to save memory, because this structure here uses a lot of memory. And one of the things that we might take advantage of is something known as a Patricia tree. And the book's got an algorithm. I happen to have it in front of me. Patricia stands for here, Practical Algorithm to Retrieve Information Coded in Alphanumeric. You don't care. I don't care. But anyway, just so you know, the Patricia tree is not named for someone's daughter. This word Patricia is actually an acronym for the purpose of the tree, and so that's in your book. It's a little curiosity if you're interested. The idea here is, if we look at a structure like this, we take note, perhaps, of the fact that, actually, let me go ahead and make these null. We take note of the fact that on level 2 here, for example, the only pointer that is active is the R pointer on that particular node. So any single words I have in this trie that start with CA also start with CAR. And so, in other words, in terms of searching down the tree, this node doesn't really contribute anything of significance. If I say, well, if it starts with CA, it also starts with CAR, the point of these nodes is to help us make choices, to say, well, now that I have, on level 1 here, everything that starts with C, these things are the ones that start with CA, and these are the ones that start with CO. When we only have one pointer active in an array, it's not really giving us any information. It's simply saying move on here, and I could just as well have jumped straight from level 1 to level 3 here. As long as I knew I was skipping over an R, if I held that character somewhere, I could then say, well, I'm going from CA, and I know anything that matches in CA also matches CAR, and now the question is it CARD or CART or CAR null, or whatever. So it's much like the B tree, where we said once the root underflows and it's down to only one child, then the root wasn't contributing anything to our decision making. We said, well, any choice that takes us to the root will automatically likewise take us to the node after the root, because the root only had one child. And so as a result, we say, well, what purpose did the root serve then? We are doing this whole discrete and not getting a helpful choice out of it. And likewise here, we're saying we go from node 1 to node 2, but there's no helpful choice made there. So it would have been handy in terms of saving the space of that node if we just jumped from 1 to 3 directly. And so that's the idea behind the Patricia tree. The concept here will be that don't store nodes have only one non-null pointer. We don't want to store nodes that have only one non-null pointer. And so in the tree we looked at, here's an example of a non-null one non-null pointer. This node was, this node was, this node was. In fact, in this tree, the only useful nodes were this one here, which had 2 pointers active, this one had 2 pointers active, and this one had 2 pointers active. And everything else simply had 1 pointer active and could have, in a sense, been skipped. Now, we have to skip things carefully so we know what we're doing anyway, so I'm going to draw an abbreviated version of the trie that appears on page 261 of your textbook with scientist names. I'm going to draw this as a trie first, but I'm not going to have room to draw the full array structure here. So I'm just going to sort of draw some circles and some letters here. And so you have to bear with me that it's a bit abbreviated so I can fit it on the one piece of paper here. So here's our root pointer. And let's say here we have M and P on level 0. And then we have here A and E on level 1. And then the A, here's where I'm going to sort of abbreviate things, goes to X, W, E, L, and L. And the E goes to N, D, E, L. And then we have a split here between L and null. And then that continues further down, and this then gives us the name Mendel. And then this P goes to A and L, or I'm sorry, V and L and O and V. Because and then this goes to null, and that null goes to Pavlov. And then further down we have here a null, and then this goes to, and now this is getting a little harder to read, Maxwell. This is eventually going to point to the name Mendeleev. And like I said, I can't really fit everything on the piece of paper here. What I want to do for you first is illustrate the expanse of this trie, and this only holds three of the names the book held. But the idea would be here, if these were the four names we're holding, Maxwell, Mendel, Mendeleev, for which Mendel is a prefix, and Pavlov, name of four scientists. This would be the kind of, just kind of sketching it informally the way the trie would break down, where this node on level 0 actually breaks things down. You have a choice there between M and P. For the first character of the M subtree, for character 1 of the M subtree, you have, I shouldn't say first character, for character 1 of the M subtree, you have a choice between A and Maxwell, or E for Mendel and Mendeleev. And then once you have the A from Maxwell, well, there's only one word that starts with MA, and so you only have one pointer active for all the rest of them. This level 2 pointer, there's an X. For the level 3, there's a W. For level 4, there's an E. For level 5, there's an L. Level 6, there's an L. Level 7, there's a null, and then Maxwell would be on level 8. And likewise here, for level E, for E here, we say, okay, you've got M on level 0, E on level 1, and then once you've got that E, you've got then N on level 2, D on level 3, E on 4, L on 5. And so everything that starts with ME, for sure, there are things that start with ME, there are things that start with MA. But once you know you're dealing with the ME subtree, then you have for sure NDEL in characters 2, 3, 4, 5. and then you have then once you hit level 6, now there's a choice. This should have been an E, not an L. My mistake. As you can see here, after the L, there's an E. So we had here on characters 2, 3, 4, 5, N, D, E, L. And then character 6 was either an E or a null character to end the word Mendel. And so the E would have been pointing to other things, and the null we would have pointed to here an E, and then an E, and then a V, and then a null, and so on. Or I'm sorry, we would have pointed to one E, and then an E, and then a V, but I can't fit it on the page here. And then the null character points to Mendel. And then here in Pavlov, we would decide between M and P on level 0, but once we enter the starts with P subtree, there's only one word there. And so we have one pointer nodes all the way down to the null character, which points to Pavlov. And so that's a lot of memory wasted. And if you kind of take a quick glance at things, only the circled nodes are really making decisions here. And all these nodes here, and all these nodes here, and all these nodes here aren't generally useful. So what I could do is I could write it like this, and this is the Patricia tree form, which now I can sort of draw in full. I have the root node here. I say here, here's the M and the P. And I don't need the A node, the V node, the L, the O, the V, and the null. They're all just one pointer in each of those nodes that is active, that is not null. So I can just here point directly to Pavlov, which would have been 1, 2, 3, 4, 5, 7. If you were inclined to keep track of the level of the leaves, which you don't necessarily have to do. You will, in this case, need to keep track of the level of the node itself, the non-leaf nodes. We wouldn't have needed to do that in the original try because we could have just kept track of it as we went. Since every node on every level was kept track of, as I traverse from level 0 to 1 to 2 to 3 to 4, I could be passing a level parameter that I simply augment with every subsequent, recursive call on the next lower subtree, or every loop iteration or whatever. So I could keep track as I go down level by level of the level I'm on. I don't need to store the level in the node, even though it might be helpful in certain times. Where here I'm going to need to, because I'm going to be skipping over certain levels. I can say here, well, I need the level 1 node because that divides between the MA subtree and the ME subtree. But now that I have an MA, well, there's only one word that satisfies that condition, Maxwell. And that is going to be on level 8. I can store that. And as far as the ME stuff goes, I don't need another dividing node until level 6, where I'm dividing between E and null. And if it's null I'm after, then I can store here Mendel, which would have been a level 7 node like Pavlov. Would have had M at 0, E at 1, N on 2, E on 3, E on 4, L on 5, the null character on level 6, and then your leaf on level 7. And then here, this would have been now Mendeleev, which would have been level 10, because we have the E here on level 6, E on level 7, V on level 8. The null character would have been on level 9, and then that leaf would have been a depth of 10. And so given this try, which I wasn't quite able to finish the nodes for Mendeleev, but I would have had another E and a V and null and then the leaf. This is the Patricia tree format of that same try. And as you can see, it cuts down the memory usage significantly because all the nodes that had only one character are gone. Now, we might also want to store the substring we've skipped. We need to store the level because I need to know here, when I go from this node to this node, what I'm now comparing is the 6th character of my string and not the 2nd. So if I'm looking for meet, M-E-E-T, I shouldn't find it here because I'm not saying, oh, the M pointer is active and then the E and then the E. This E, the 2nd E, is not meant to be character 2. So if I'm looking for this word, I shouldn't find it because this E is not character 2, it's character 6. And we'll need to store the level this time so that that's clear, that you can say, well, given the level of this node, check out that particular cell. And there is, of course, no cell 6 here, so that word doesn't exist in this try. But as far as the rest of this goes, if I'm going to look up Mendel, I say, well, M is character 0, and I can follow that pointer. E is character 1, so I can follow that pointer. Now I'm supposed to be looking for character 6. Mendel has a null in character 6. I follow that, and then I get a leaf, and sure enough, that's Mendel. And so that would be how we would do a lookup. We would need to, we'd look up the characters we do store, and then we would proceed to then check if the string matched. And so if I was looking up, for example, Mende, which of course isn't a word, as far as I know. Monday is, but this is Mende. I will say, hey, the M is character 0, and I do have that pointer active. And the E is character 1, and I do have that pointer active. And the null is character 6, and I do have that pointer active as well. And so now that I've matched the M and the E and the null, I now am at a leaf, and I can proceed to then compare the characters in that leaf string to the N, D, A, and Y to see if now the stuff I skipped over in characters 2, 3, 4, and 5, does that match as well? Or I can just do a general string compare of what's there to there. So it's that I've got a match of the characters that my tree stores, I've got a match with what's in that leaf, but I skipped over some characters as well, and I need to worry about matching those. So now at this point, once we get down to a leaf, once we know the null character is active, we don't know for sure that we found the word yet. All we know is I've matched the characters I have looked at, and I've matched the null, but I don't know about anything else. And so in general, once you get to a leaf, you'll need to be now comparing your lookup string to what's in that leaf to make sure that you really have found the word, as opposed to just a word that matches in the characters you've stored, but not in the stuff you've skipped. And here we don't match everything we've skipped. We match the N and the D, but not the E and the L. Now, you may take a while to get down the leaf. Maybe I skip characters 2 through 6, but then I have 6, 7, 8, 9, 10, 11, 12 until I'm down to a leaf. And I might not want to traverse all that way down to get to the leaf. And so if the only place I'm storing the characters I skipped is in a leaf, I would have to traverse down to a leaf to find those. So if I'm comparing Mendeleev to maybe some larger string, and I have maybe 3 or 4 more levels before I reach Mendeleev, and now I'm comparing it to something that differs in characters 2, 3, 4, and 5 from Mendeleev, but matches in all the other characters. I'll match in 0, 1, 6, 7, 8, 9, 10, whatever, and then I'll finally get down the leaf and can then do a compare to find whether the characters I skipped over would match as well. And I might not want to traverse all the way down that far. I might like to know at node 6 if I match in these skipped characters, rather than having to traverse however long it takes to find the leaf before, in this case, I can find a leaf right away, but that might not be the case all the time. I'd like perhaps to know at node 6, these are the characters I skipped, let me try and match those as well, rather than having to search even further down for a leaf and then reading the skipped characters from there. And so in that case, we might find it helpful to store with the node a substring of whatever we've skipped. And so here, since I've skipped levels 2, 3, 4, and 5, I have here then N, D, E, and L stored. And each character here might take only 8 bits. And so together, those 4 characters will only take 32 bits to store. And I've saved the node here. I've saved 27 pointers per node. Each pointer takes 32 bits, and I've saved 27 times 4 of those bits. So I've saved here 108 pointers at 32 bits each. And the consequence of that is I need to store 32 bits worth of characters. And that's a nice trade-off. Get rid of 128 32-bit words, and then use one 32-bit word to indicate the 4 characters you skipped. So even though we're storing here the 4 characters, that's still not chewing up anywhere near as much memory as those 4 nodes would have chewed up that we've skipped over. And so in that case then, I can say M is active, and E is active, and then come down here to level 6, and I say, well, let me, since I've jumped from 1 to 6, let me read the substring of this node and check those 4 characters to see if they match. And if they match, I know I've matched in the skipped characters as well, and then I can proceed and check character 6. So that's one way to do things. Rather than having to search down a leaf, you could indeed store the skipped substring inside this node as well. Oh, that's the Patricia tree. Now, when it comes time to insert into this structure, it's not much different from inserting in the trie. You just have to take care of, knowing what levels you're skipping. If we come back to the trie and I wanted to insert something new, all I would do is activate a pointer that wasn't null before. So if I wanted to insert, for example, the value cart, well, I could simply say C is active already, A is active already, R is active already, T is null, I simply make T active. And I would have T pointing to some node. And I can't quite fit it in the picture anymore. But all we would do here is we would say have T point to a node, and then we'd have the null character there point to a node, and then that would point to that null, the null character then would point to, I can't write the word in there, but it would point to cart. So this would be our leaf, and I'll just sort of darken it in as a circle. Like I said, the tree is just too complicated to draw anymore. I only have so much room on one piece of paper. But if I wanted to insert cart into this tree, I'd simply traverse down to where the word was prevented from existing. And if I never had that happen, then the word would have already been there. If I wanted to insert car, I'd say that's C-A-R null, and hey, wouldn't you know it, all the pointers were active, and I ended up with the leaf holding car. So there you go, you're done. You don't need to insert it, it's already there. If the word isn't there, I'm going to hit a null pointer sometime. Whether I, say I'm the word to, for example, T is active and O is active, but the null pointer is not. And so if I want to enter the word to, T-O, then I'd activate this null pointer and make that point to a leaf holding to. And likewise, if I want to insert cart, C, A, and I are active, the T is null, I have T point to a new node instead, and then that would be all nulls except for the null character, which would point to your leaf. So inserting into a trie is simply a matter of traversing down to the null pointer and then inserting the needed nodes one by one starting there. Inserting into a Patricia tree is much the same way. All we need to do is insert a new node in between. So let's say we want to add Mende. If we have this structure, and I'm going to sort of just leave this to kind of show what's going on here. This was your node. You had here an A pointer and an E pointer. And that E pointer pointed down to a level 6 node where you had E and you had null. And here you had Mendeleev, and here you had Mendel, and you maybe perhaps store the N, D, E, and L here as well. Now if I'm trying to insert the made-up word Mende, I can say, well, I would have matched in the M, and I didn't draw the M node up here, but I would have matched in the M, I would have matched in the E, and so I'd be at this pointer here, and I'd say, okay, I notice at level 6, I've skipped over N, D, E, and L, and I matched in characters 3 and 4, but not in 5 or 6. And that can be a problem. And so what I need to do here is say, well, I still match in characters 3 to 4. So I could continue to skip over those, which means what I need here is to have a new node on level 4. And I say, I still skip over ND, but now this node will have the A pointer active, so I can point to Mende. And it should have the E pointer active, so that I can point to the Mendel and Mendeleev. And now this gets replaced with just L. So I now have, then I need to say, well, now this points to here. So now when I look up Mendel or Mendeleev, I'd say, well, I have some M pointer coming from level 0, and now the E from level 1 points to this level 4 node. I've skipped over N and D on levels 2 and 3 if I'm looking for Mendel. I look up the M, which I haven't shown, follow the E pointer, skip over the N and D, follow the E pointer here, and then I skip over the L, and I follow the null. If I'm looking for Mende, I say, well, I didn't show the M, follow the E, I've skipped over, in going to this node, I skipped over the N and the D. For character 4, I follow the A, and there's Mende. Or in other words, what I've essentially done is NDEL used to be the skipped over string. Now with Mende, N and D can still be skipped over, but the level 4 character, A, is different from the former level 4 character E here. And so as a result, I can still skip over N and D on levels 2 and 3, but I'll need to insert a node on level 4 to divide between E and A. And that's what's happened here. I said, well, this, because I matched in 2 and 3 with what these were, I can still skip over that. But level 4 for these words, as indicated by that substring, is different than level 4 here. So I insert a new level 4 node to differ between the A and the E. Then whatever was between level 4 and 6, I continue to skip over. And so there's my the former NDEL that I skipped over. I'm still skipping over all but one character of it. I skip over levels 2 and 3 to get to this node. I skip over level 5 to get to this node. And I simply do need to actually represent level 4 now. So N and D are still skipped over, L is still skipped over, but the E is not skipped over because the E and the A are two different characters on level 4. And so we need the level 4 node to distinguish between them. And so again, storing the skipped over substring makes that a little easier to deal with. But that's how you'd insert into this try. It's almost like a linked list insert where you create a new node, point the next pointer to the old node, and then point the previous node to the new node. And where in the other try, you were adding a bunch of nodes. Here, because you skipped over particular nodes, you have to go back and insert them in between when needed. With the original try that held every possible node you needed, that wasn't an issue. But that's it for Patricia trees. The other possibility, the other thing we'll worry about from Chapter 8, Section 2, is known as the De La Grande tree. And the De La Grande tree is simply, all we're going to be dealing with here is using sparse array implementations of our lists. So when I was storing, let's go back and store now car and cart and all those, I simply say here, my root pointer here, instead of pointing to an array as we did originally, we pointed to an array with the C and the T pointers active. Instead, I'll simply point to an array, or I'm sorry, a linked list, where we have here the letter C, and the letter T, and then the pointers on those linked lists will point to the respective subtrees. And so on level 1, I had CA words and I had CO words. And so I can say, well, here on level 1, now this will be pointing to a linked list that has CA active and CO active. And level 1 here simply had O active. So all I need here is to be pointing down to some list containing O and nothing else. And then we'll just continue from there. So that we had CA, and then at CA we only had one choice of letter, which was an R. And when we had on level 3, we had a choice here on level 3 of card or CAR null. And so this is where we pointed to our car leaf. Card pointed to a level 4 null. This is a D here. It's hard to distinguish between D and null now. And card pointed to here. And then the O here pointed to a W node, which pointed to a null node, which pointed to my cow leaf. And likewise, the one here pointed to top, pointed to a P node, and that pointed to a null node, and that pointed to top. So it's the same structure as the original try. This was my original try, ignoring the insertion here of top and 2. This is my original try. This is the De La Brande conversion where every array has been turned into a sparse array. So instead of holding 27 pointers, I hold a linked list of the non-null pointers. And there are only 2 of them in some of the nodes and only 1 of them in the other nodes. And so if I want to find t now, I can't jump directly. I can't say, well, extract the letter top. I find out the index from the corresponding index would be 19, and I jump straight to cell 19. No, now instead of converting the letter to an index, I search down the linked list trying to find the letter t. And when I find it, I then traverse down that that subtree. Otherwise, if I'm looking for w, for example, in this picture, I would have, for w, which would have been 22 for index if we started at 0, I would have jumped straight to cell 22 and found out it held null, and I would have said, no word starting with w. Here, I would search the linked list for w, and I would not find it. I would hit the end of the linked list, the null, before I found the node containing w, and so I'd know w isn't there. And so that would be how I would deal with this structure. And so given that setup then, the only difference between this and the regular try is, well, this obviously saves a little bit of memory if you have small lists. If you have, really large lists, you're now storing 2 pointers and a character in every node. So once these lists become, a certain size, they don't need to be 27 nodes long before you're using more memory with a linked list than you would be with the plain old array. But as long as the linked lists are relatively small, you're saving memory here. On the other hand, as the linked lists grow, it's also going to take you longer to search down them. So this is effective when your lists are small because you still get somewhat close to constant time on each level because it doesn't take you too long to search down a list. If the list is 13 or 14 characters, it takes you longer to search down the list than if it's just 1 or 2. And so as these lists grow to 12, 13, 14 characters, it's difficult to say you've still got constant time on each level. If the list is only 2 or 3 characters, it's still not too bad on each level. And so that would be the idea then. If your lists are small, this saves memory, but at the expense of, it does require a little bit more time on each level. And the longer the lists grow, the less memory you'd be saving anyway because, if you have an array of 27 pointers and 13 of them are not null, that's a little bit better than if you have an array of 27 pointers and only 1 of them is not null. And so if you have actual 13 useful pointers, you're not wasting quite as much memory with the array, and the linked list of 13 pointers would be holding as many pointers as the array would be anyway. And so as these lists grow to, say, size 13 or so, for the English alphabet anyway, the list isn't any better than the array, and it's also taking much longer to search down than the array would to access the index directly. But it's a trade-off when you have small lists. And so that's the only difference between the De La Brande tree and the regular try is that you've now got lists in place of the arrays in each level. And of course, you could make a hybrid structure out of these. I could just as well have use the optimizations of the Patricia tree and the De La Brande tree. And I could have said, well, this was my original Patricia tree. This is the picture I had put up with. And I could have said, well, what if those 3 arrays were linked lists instead? We could have had a structure that looked like this, where I have root, and I have here 0, oops. Here I have M, and here I have P. And the M and the P pointers are here, and we point to Pavlov right away. And I point here to a list containing the nodes A and E, and the A points to Maxwell right away, and the E would point to now a level 6 linked list containing E and null. And again, we'd need to store the level here, and we'd probably also want to store what we skipped, some sort of substring of what we skipped. But anyway, we'd point to E and L, or E and null, and then the E would point to Mendeleev, and the null would point to Mendel. And so from this Patricia tree, where we have 3 arrays and 4 leaf nodes, we could have converted it to this De La Brande tree, where we have 3 linked lists and 4 leaf nodes. And so that would just kind of be adding both optimizations if we expect all the arrays to be ones in which that we have a relatively small number of values. Instead of looking at it like a Patricia tree where the array's been made sparse, we could also have looked at this like this is a or I didn't actually draw the picture here. If you drew the De La Brande version of this, you would see that you'd have now just here, just as we have here, the De La Brande version of the nodes we inserted. We had the R node had only 1 pointer. All these nulls had just 1 pointer. The O, the P, the W, those were all sort of useless nodes that had only 1 pointer, 1 linked list node, instead of here where we have 2, or here where we have 2, or here where we have 2. And so likewise, if you had drawn just a pure De La Brande version of this, you would have had, you would have had a X with, X node and a W node and an E node and an L node. And so what you're doing here is saying, take the De La Brande tree and then get rid of all the linked lists that have only 1 node, and this is the picture you get. So you can view this as the Patricia tree with the arrays made sparse arrays, or picture it like the De La Brande tree where we get rid of all the linked lists that have only 1 node. Either way, this is what you end up with, the combination of the two. And you can also have sort of done a hybrid of all 3 by saying, well, if you think about English words, in the dictionary, every single letter starts some words. So we've got, for example, here we can say, well, I can say you have S and Q and X and T, and all of those letters are starting letters of some word. But on the other hand, we do have some suffixes like, or prefixes like SO and SL, and there is no QJ, there is no XR, there is no TQ. So these are prefixes you would actually have. Those would be prefixes you wouldn't have. The point being that if I was to draw a array that was going to hold all, or a trie that was going to say hold all the words in the English language, I might well want the top array, or the top node, to be an array, because I might expect that node to have all the pointers active, and I might even choose for level 1 to be an array as well. So we may have here A and E, and then here I have Maxwell, and then maybe after level 1 I say, okay, now I expect very few pointers, because when we start talking about length 3 prefixes, very few of them actually exist in the language. And so maybe I say, well, now I expect that from like level 2 or level 3 onward, there's few enough possible prefixes that I don't expect any linked list will have that many, or this was P, that many values. So this is sort of the, if we do it this way, here's Mendel. This is sort of the combination of the regular trie with the Patricia tree optimization and the De La Brande tree after a certain level, where I say when I expect to have many pointers active, I will use an array to deal with that many pointers. And in the lower levels, where I don't expect to have too many pointers active, I could use a linked list instead, because I expect it'll be quick to search down, and using a linked list of 2 nodes instead of an array of 27 pointers, all of which but 2 are null, will save me some memory. So I can actually do a hybrid of all 3 of them and basically say after some certain point I'll continue to use an array, but when the array only has very few nodes active, I'll use a linked list instead. And then when the linked list exceeds a certain number of nodes, it's more efficient to use an array, and I go ahead and use an array. So that would sort of be a very nice structure then for looking up individual words. We've more or less got a hybrid of all of these together. And so by looking at the basic trie idea and also adding the De La Brande tree optimization where appropriate, and making the whole thing a Patricia tree, we have a very nice, fast structure for looking up words. We're looking up each word, or something that can be broken down into characters. Looking up each one of those items does not depend on breaking down items. Does not depend on how many other items are located in the tree. And so that's the idea behind a trie. There's not much more to say about that. There's other things in section 8.2 as well, among them a different kind of trie implementation and also something called a digital search tree, but don't worry about that. Just worry about what I've gone over here in lecture. And that's it. I will see you next time for graph implementations. See you then.